today. Very short talks actually, because we wanted to fit in as much as possible from all the applications. Hopefully next year we get the full day again, which would be great. So we got different topics like graph streaming, graph analytics, graph querying, so all things graph, which is cool. And yeah, with that, I want to introduce our first speaker, Vincent from Intel, who will talk about scalable cross-platform graph analytics with Python. Go ahead.
So hi everybody. So my name is Vincent at Intel on Hive, which is not an acronym for Scalable Cross-Platform Graph Analytics Framework in Python. And this is work we are doing conjointly with Anaconda. So quick outline, what is Hive, what is the architecture, the interfaces, how do you extend it, and a quick summary of it. So at its core, what we're trying to do with Hive is to build a graph analytics API in Python for graph users. And because you're operating in Python, you probably want to do integrate into that whole data science ecosystem, right? And the kind of interoperability we want to provide is that it's easy. For instance, if you have containers like NumPy, arrays or data frames, you can use them, convert them into graphs. Right? So this sort of already exists if you think of NetworkX. The issue with it is that it's pretty slow. So one of the things we want to do is really leverage all the fantastic high-performance graph libraries that are out there, right? So that it's some people it's their bread and butter, right? They do their research, they maintain it, they make it perform. Once you have these APIs and then a set of graph frameworks, you need some kind of a glue, right? Something that can orchestrate how do you go from this Python API down to actually calling into some implementations, right? And for this, we're going to use that, which is developed by Anaconda. We want this to be a community-driven effort, right? So there's a number of data science packages, there's a number of high-performance graph libraries, and we can't just tackle everything by ourselves, right? So we want to give out the frameworks, the interfaces, and have people contribute to it. And finally, we want this to be hardware agnostic, so we want to be able to plug as many hardware vendors hardware in there, but do nothing in that architecture that would make it that you're locked into some ecosystem. Finally, this is in development right now. Think of this as a kind of a teaser of things to come. And it's going to be open source in 2020, sometime with like the 0.something, to get feedback from the community. So let's start at the basics, right? So if you want to express a graph algorithm, right, you're going to have to need data for graph representation. And you're going to express your graph algorithm using a paradigm, right? So think of this, for instance, you can express a graph algorithm with linear algebra. You can use vertex-centric, synchronous kind of model where you have data from your neighbors, eccentric, all this. Right? So someone is going to provide you with an API, and you follow that paradigm, and then you can implement your graph algorithm. And finally, you get your data in the compute. Right now, you need the hardware architecture that you can run from. Right? So all of these things are interrelated. So this is an example, just a list of graph frameworks, right? There are no way associated with this effort. I just picked them because people doing great work, just to illustrate my point. So if I take, for instance, SureSparse, right, I'm going to have basically using a subset of this graph representation and a certain way of expressing things to write my graph algorithm, and then targeting a certain architecture, right? And this is basically just because people are focusing on something, and it's not a critique, I guess that's what I mean. But if I switch to Galois, then I might have a different set of things I'm going to use and graph it and so on, right? So the question is, if I'm a data scientist and I'm sitting in the Python ecosystem and I want to leverage this, how do I do that, right? So if you have a Python interface to one of them, you can use it, but then you kind of are buying into a small ecosystem, right? You have to maybe format your data so that the graph algorithm can use them. And if you're building a workflow, maybe there's something in one of these frameworks that's not available in the other, and now you have to deal with how do I go from one to the other. So this is where we think the Hive API would contribute. So the goal is to have a high-level set of graph APIs. So think of this like you want to do community detection clustering, so you can use Louvain. You want to do some graph pattern matching, so you have subgraph isomorphism, this sort of thing. So very high level, so that if you're a data scientist, you can just take it off the shelf and use it. One thing we want to explore is doing this kind of a graph APIs with Numba. So if you're not familiar with Numba, it basically allows you to write a function in Python, and you annotate it, and then you can cheat it. So one of the simple things we wanted to try to do, for instance, if you want to do some kind of a filtering operation, you stay in the Python side, you write this kind of a predicate, and then you have the runtime go over on the edges or the vertices, apply that function, and you get a subset out. And finally, we want to make the interoperability easy with the data science system. So think of this as how do I convert across containers, what are the most popular things we can sort of support by default so that other people don't have to. So once you have these APIs, you need a glue right, in between the APIs and the frameworks. So we're going to use the Dask runtime. So think of this as you do lazy evaluation on the APIs, and you dynamically build this task graph with the things you want to do. Right? And now you have the user express what he wants to do, and you also have a bunch of graph algorithm implementation that advertise themselves. So you need a broker to do the orchestration, right? So this is both. I want to schedule the compute on resources, and also I want this runtime to handle all data movements. And finally, we want this to be accessible via plugins, so that you can just sort of jump in and add your own things. So let's have a look at the framework interfaces. So the centerpiece is this Hive Dask runtime, right? So it's going to be orchestration. Then you have the user API. So again, high-level thing like do Luga on the graph, and the graph is kind of this opaque type, abstract data type. Right? It's just a graph. Then you can define your data models, right? So for this abstract type, that's a graph. I want a concrete type, which is maybe I have a data frame that represents an adjacency matrix, and it's stored in the CPU memory subsystem. And I also have a CSR data type, right? Anything I can imagine. So then you're going to define transformers, right? So how do I go from that data frame on the CPU to a CSR on the CPU, and so on. Right? So some of these, they can be part of a common library, and some of them, the framework implementer can go and add them. And finally, you have the graph algorithm backend. So think of here, I'm saying I'm exposing Luga. It's running on this XBlast framework that I just made up, running on CPU and taking a CSR as input. Right? So when you think of building all of these, right, you actually just built a graph of dependencies, right? So this user API, they have implementation as graph algorithm. They use some data models. These edges between the models, they are the transformers. So Dask can now take this graph and reason about what the user has expressed and what he can do. So it's really doing graph analytics with the help of graphs. So on the left-hand side, you can see a workflow of a task graph. So here I start outside of the Hive ecosystem, right, loading data, pre-processing, whatever is your workflow. And then once you cross in, right, you can say, I want to create a graph, I want to apply an operation, and so on. So if you think about that graph we had before, dependencies, right, here I might have a data frame coming in here, right? So the system knows, okay, I have a data frame data model, and what do I need to convert it into? Well, it depends what is the set of graph operation implementations I have. Right? So solving this, and you come up with basically a schedule. And finally, when you, at some point you just exit that and go back to your regular workflow. Another cool thing here is the data transformation. So just by transitivity, you might actually support some stuff that you haven't provisioned for. So here, for instance, I start in a file format. I know how to make it a table. I know how to make it a second graph format into a last one. So would probably run horribly, but what I found pretty cool about this is that now you can think about building some performance monitoring infrastructure, right? So in Dask, you could look at this graph and kind of figure out, you keep doing this path that is very long and expensive. So the system could tell you, hey, if you actually implement a conversion directly from that file format to that graph format, then you're saving time. Same thing on the task graph. You could think of for different graph inputs, you could try and characterize them and and then you could see when you run on CPU, when you run on GPU with these different inputs, this is the results you have, right? So you could plug all of this into some machine learning framework and basically learn from that. So in terms of extensibility, this is how you would support new hardware. So as you see, there's no functional changes to the user API, right? So you basically, the only thing you might do is just maybe add annotations to say, I really want to use that new backend that you've provided, but you don't change your code. So transparent for the user, mostly. And then you only need to implement these plugins, right? So I need to go and describe the data model for the CSR on that XPU I made up, what are the transformers, again, and finally my implementation. So here, this is an example where I use a framework and I just extend it. But what I find pretty interesting is that you could just take any code off the shelf from internet that's using pthread or whatever, you wrap it in that Python interface, and then you have it advertised in the framework. And it's a great way to basically leverage what's out there. And once you've done that, then it's part of the high runtime toolbox. It makes this graph we've seen larger, and then you can use it. So one thing that's pretty cool also is that allows you to mix hardware architecture, right? So you can start your, if you have different graph operation, maybe you did one on the CPU, the next one on the GPU. It's also a great way to get portability, right? So if today I'm running on a box and it has a GPU and I'm using the GPU algorithm, but tomorrow I'm not, as long as I have an implementation that covers the CPU, my code would still run. So in terms of the extensibility for if you want a new user API, then it's the same thing, you just have a subset of plugins you need to work with. So the user API, so here I'm extending it as that I want triangle counting on a graph, and then I just have to provide at least one implementation, right? So here I'm still using my last example, and then again it's just going to be part of the API of the runtime toolbox, right? So we run this basically so that people can just plug in new algorithm and leverage all the work that's been done on the back end. So as a sort of a summary for the stakeholders view, if you're a data scientist, what you gain is that you have now a unified API for graph analytics. You have the Python interoperability that allows you basically to plug your work into a larger workflow. And basically you just have these state-of-the-art backends that are always available, right? They are maintained, they are optimized. You get the transparent orchestration so that you don't have to worry about what is the actual underlying hardware you have. And you get the increased workflow portability. If you're a graph framework developer, we hope this would help sort of structure a way of this is how I present a graph algorithm in a Python form. So hopefully this would sort of bring the community together. It's an increased user base, right? So now, because it's much easier to plug in the framework into that larger Hive ecosystem, hopefully that would grow your user base. And what I really hope we can do is some way to provide performance feedback for the people who are developing this, right? So through that, by logging and sharing those data. And finally, if you're a researcher, I guess in the grand scheme of things, we want it to be easy to integrate in your workflows, right, across the Python ecosystem, and be easily extensible so that people can do research, either at the orchestration level or the data model, or the frameworks, and basically have this performance monitoring and optimization to improve the codes. So that was my presentation about Hive, the bridge between graphs and data science, and I will take any questions.
Somewhere where optimization, not to
think it's you can definitely do that. I think part of the work would be also to instrument so that you kind of learn what is the performance characteristic of running something, right? So that because then when you have this data, you can make decisions, right? So it could be very well that in some cases, even though you ship data back and forth, your accelerator is so much faster that it makes sense. In some cases, it might not. So if you have the data, then you can make the reasoning. Yeah, I think at the DAS level, basically, whatever is the orchestration plugin, that's why you plug in heuristics, right, of how you should. Most likely this would be also policies that you can just inject. So for some reason, depending on what you want to do, say, favor this and that approach.
One of the sort of conditions that you had was you could be able to have any hardware and then run an algorithm on the CPU and then another one on the GPU. Who do you expect in that scenario to handle that data movement going from the CPU to GPU?
Yeah. So the question is, who do you expect would be doing basically the data movement between CPUs and GPUs? I think it goes a little bit into how this effort would fit in the ecosystem, because some frameworks, right, you have one entry point and then it kind of decides that their own heuristic to say, do I do CPUs or GPUs? So I think what we would need, ideally what we want is, as we build that task graph, we would like DAS to have the control, basically, to have the most flexibility possible. And for that, you kind of have to open up a little bit these frameworks to say, it's not just that I'm doing Luda on a graph, I'm doing Luda on a GPU or Luda on a CPU. And at that point, then in that these data transformers, right, because it goes back to that question, right? Then you have the whole picture and you can say, okay, it would cost that much to do the transfer, and you can actually do something about it because it's not baked in the framework. So then you have these data transformers that would basically